Hi guys, my name is Vinay Jain and today we're going to talk about depth first search algorithm for tree traversals using stack. So let's say this is an example tree that we have and root node is the node 1 at the top. So how does depth first search algorithm work for this tree? So as the name suggests, depth first. So for every node it goes into its depth, that is in its child nodes, and visit them first, then in their child nodes visits them first, and so on and so forth, until and unless it has completed its depth it keeps on proceeding. So let's say here we are here at node 1. So does it have a child node? Yes, left and right child node. So we visit the left child node first. We check here, do they have child node? Yes. So we visit the left child node of that child node, which comes here. Do we check here, does this node 4 have child nodes? No, it doesn't. So we go back to this node 2 and check if there are any further child nodes to be explored. Yes, there are. So we explored that depth and visit here. No further child nodes to explore at node 5. So we go back at node 2. Then no further depths to be explored. No further child nodes to be explored. So we go back to node 1. We check here if there are any further nodes to be explored. Yes, there are. So we go into this direction in this depth to explore the child nodes. Check if there are any other child nodes to be explored here or not. Yes, there are. So we proceed in that depth. No more child nodes to explore for this node 6. So we go back to node 3 and explore node 7, says that is the next unexplored child node. Then we move on to 10. Then we go back to node 7. From 7 we go to 11 into further depth. And then we visit this in this order. We visit node 12 first. From node 11 we get the control back, and then we visit node 13. So this is how the algorithm works. So let's understand this algorithm via dry run. So let's redraw the tree. 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13. Note that we're working with binary tree. That means every node in the tree has maximum 2 child nodes, and the order that we're going to use of working with the children nodes is, first we're going to work with the right child, and next we're going to work with the left child. You can do it in any way. This is the one that I'm choosing to work with. And since we're working with a searching algorithm, right, so we need to search something. So the target that we're looking for is node 13. So this is what we're looking for in the tree. And as said earlier, this is the root of the node of the tree. Sorry. In BFS we use queues to keep track of the nodes that we're traveling. In DFS we have stacks. So stack is a data structure which works on LIFO, which is last in, first out. So whatever is entered in the end, that is the first one to come out. We'll understand this much better via an example. And then we have a pop node. This is a variable in which basically tracks the current node that we're working with. And we have a visited set. This again is to keep track of all the nodes that we've visited, so that we don't keep visiting them again and again. So let's say this is how we have a stack and pop node variable and visited set. Yes. So let's do a dry run of this algorithm. So we first push the node 1, the root node, which is here, to the stack, and then we start iterating as long as the stack is not empty. Currently the stack is not empty, so whatever is at the top of the stack is popped out. So the top of the stack is this node, so that is popped out and assigned to pop node. Does the pop node have any children? Yes, it does. So what are the children? Node 2 and node 3, right? So those are the further next depths to be explored. So as I said, this is the order that we'll be working with: right child first and then left child. So we push the right child first onto the stack, and then we push the left child onto the stack. Now we add the pop node to the visited set, since there are no more depths, no more child nodes to be explored. Now we go back again to the stack and see what is the topmost node. So the last node that came in was the node 2, right? So this would be the first one to come out since this was at the top. So node 2 is popped now and assigned to pop node. Does node 2 have any children nodes? Yes, 4 and 5. So we put the node 5 first, as it is the right child and the left child of node 2, which is 4, and add node 2 to the visited set, saying that we have visited node 2. Notice that we started from node 1 and then visited node 2 in the next depth order. Next, we go back to our stack, pop the topmost part, which is node 4, assign it and check if it has any children. It doesn't have any children, right? Node 4 doesn't have any children, so we just add it to the visitor set and don't add anything to the stack. This essentially means that now after node 2 we have explored node 4. We have gone in this section. Now what is at the top of the stack? Node 5. We pop it, assign it to pop node, check if it has any children or not. No, it doesn't, so we don't add anything to the stack, and we add it to our visited set. That means now we have explored this side. So notice how we have explored the leftmost depth first, and then when the left depth was explored, we explored the right depth. So basically something like this. Now that we have understood that, let's go back to our algorithm. So what is at the top of the stack now? Node 3. So we pop that, assign it to pop node. Does node 3 have any children? Yes, it does. So add the right node first and then the left node, and add pop node 3 to the visited set. That means you have visited this part. What is at the top of the stack now? Node 6, right? That was the last to come in, so that was the first to come out when we'll be popping the stack. So this comes out and is assigned to pop node. Does node 6 have any children? No, it doesn't. So we don't add anything to the stack, and we add this to our visited set, signifying that we have now visited this in this order. What is at the top of the stack now? Node 7. We pop that, assign it to pop node, check its children. It has children. What children does it have? The right child is node 11 and the left child is node 10. We add node 7 to visited set, signifying that this is now visited in this order. Next, we pop node 10 from the stack, since that is the topmost, that was the last to come in. Node 10 is popped, assigned to pop node. Does it have any children? No, it doesn't. So we don't add anything to the stack. We just add this to our visited set, which is now signifying that now we have visited in this depth order. What is at the top of the stack now? Node 11, right? So we pop node 11 because that was the last one to come in now, and we assign that to pop node. Check if it has any children. Yes, it does. So now we visited this. So now node 11's children are added to the stack. Node 11's children are the right node 13 first and then the left node 12 first. So, and node this is added to this stack. Yes, so to the visited set, signifying that we have visited this now. Next, we pop node 12 and assign it to pop node. Is this the node that we're looking for? At every step, you also need to check whether this is the node that you're looking for or not. No, it is not. So we don't do anything. Does it have any children? No, it doesn't. So we just add it to the visited set, signifying that now we visited this part. Next, what is the node at the top of the stack? That is node 13, right? Because that's the only one left. Assign that to pop node. Is this our target node? Yes, it is. So now while we were traversing in this direction, in the next step, we found our target, and then we return true, because now we've found our target that we were looking for. So what is the algorithm for this? So this basically concludes our depth first search algorithm. So what is the pseudocode for this? So the pseudocode for this algorithm looks something like this, using stacks. So initially you have to create an empty stack and visited set, push root of tree onto the stack to begin our depth first search algorithm. Once that is done, you keep iterating while stack is not empty, while there is something to explore in the stack. Whatever is at the top of the stack, you pop that and assign it to pop node. And then you check if the pop node's value is equal to the target that you're looking for in this line. If it is, then you return true. Otherwise, you keep searching. You check now if the right child exists of that node or not. If it does, you add it to the stack. And if the left child exists, you add that to the stack. So this part is essentially ensuring depth first search approach. And stack is a means to keep track of what node is to be explored next. That is the data structure that is being used for that purpose. So you keep on iterating like this, and every time you do it, in every iteration you add pop node to the visited set, signifying that this node now has been visited, so that you don't visit it again. You keep on doing this, and if at a point of time the stack becomes empty, that means you have traversed all nodes and you've still not found the node that you were looking for. That means the node doesn't exist in the tree, and therefore you return false. So this is the algorithm for this video. I have attached the link for the GitHub repository which contains the code for this algorithm in the comment section in the description below. Please feel free to check that out.